Okay, so let's get started. So today, first we'll finish a few more examples on the method of this Lagrange multiplier, right? So for finding the force of constraint. Okay, so this is the last example that we finished in the lecture before the holiday. Right, so in this example, we want to find out the reaction force acting on this particle by the wedge. Okay. So then the next example, so again, is something that you are already familiar with, right? So but here again, we use the Lagrangian method. This time, right? So the force of constraint, okay, so that we are looking for is the tension, okay, so of the string, right? So what we have in this system, again, the only external force, of course, is the gravitational force, right? So but then the force of constraint is the tension, right? So it's because of the tension, right? So this the distance between this particle and this point is always fixed as at L. Okay. So again, so let's write down the Lagrangian, right? So the Lagrangian, the kinetic energy, and the potential energy. Right. So here we are using R and theta as the coordinates. Right. So although, right, so we know that R is actually a constant, right? So but because of the fact that we are using the method of this Lagrange multiplier, right? So we don't really explicitly put this constraint, okay, so to the Lagrangian yet, right? So we really pretend that we have two free generalized coordinates in the problem. So that's why I have both R and theta in the problem. So then the next step, I'm going to write down the constraint equation, right? So the constraint equation is this G, right? So which is R minus L equals 0. So then everything just follows, right? So and you have the Lagrangian, you have the constraint equations, then you just write down the Lagrange equation with the Lagrange multiplier, right? So I have this Lagrange equation for R and the Lagrange equation for theta, right? So and then there's really no more other tricks here, right? So you just take the derivatives and then get these two equations that are, at least for the left-hand side, you are familiar with, right? So and then on the right-hand side, you have this lambda t. Right? So and now you're going to actually put the constraint equation back to your two equations of motion, right? So from the equation of constraint, it gives this R double dot equals 0. So and then you put this back to the first equation, right? So and if you want to find out the this term, right? So this term really is the force of constraint, the tension that we want, right? Because this is the term that makes really the R is the constant. So then you can see that the force acted on the particle by the string, okay, which is tension, is given by this, and which is close to these two terms, okay, just from this equation, right? So if it is from Newtonian mechanics, right? So you also, I hope you also know how to understand this, right? So because remember that we actually going to consider the force, right? So this is the mg, and then this component over here is your mg cosine theta, right? And then this is the tension. Then the net force, right? So along this direction has to provide the centripetal force, right? So that's why this T minus mg cosine theta has to be equals to the centripetal force. Centripetal force is give you the m r theta dot square. Okay, so and that's exactly give you this. Of course, this one has a minus sign in front, right? Just to indicate that this tension is going along the smaller r. It tends to make the particle goes to a smaller r. Okay, and this one, right? Also an example you have seen. Remember that I have this smooth table, and then I have this small mass on top of the table, and then another big mass hanging at the bottom, and then these two masses are connected by this string over here. So, and that's why, right? So this Lagrangian is something that you're familiar with, right? So, but this time, as I said, right? So we are not going to really consider the put in the constraint in this equation over here. Right? So instead, the z, remember, this is the z, right? So, and this one, right? So kinetic energy for the big mass, right? So this one, kinetic energy for the small mass, and then this empty z is the potential energy for this mass over here. And then how many generalized coordinates we are using now? So we are actually using 3, right? So the r and theta for this small mass, and then the z for this big mass. And now the constraint equation, right? So right now here separately, we know that the total string is total length of the string is always L, right? So that's why R plus V minus L is 0. So now the 3 equations of motion, I'll write down over here, and then now I have take the derivative to get to these 3 equations over here. So, and up to this point, right? So as I said, you just input the constraint equation, right? So back to your set of equations over there. And last time when we talked about this example, I already also told you that, right? So this one really, right? So can also be obtained by conservation of angular momentum. And I can call this one, right, which is the angular momentum of this particle, to be J. And from there, right, so I just substitute this J equals mr squared theta dot, and this r double dot equals minus z double dot back to my set of equations. So then you are able to find out the relation between the tension, right, so and the motion of the particle. So this one, right, so especially the bottom one, right, so this one should be easy to understand, right? So because this tension, right, so and minus mg has to be providing the acceleration for this mass over here. Okay, so the next one, actually, I want you to, I'll talk about it, but I want you to try to spend a couple minutes to do it by yourself. Try to set up the equation. Okay, so this is actually a problem from the textbook. Okay, so just use the Lagrangian method. Okay, just do it that way. Okay, so what is this problem? Okay, so we have this hemisphere. Okay, so of radius a, and then I put this particle, okay, on top, and then just let it slide down like this, right? So initially it is over here. You release it from rest, right? So let it just slide down, okay, and then it will just move on this surface, right? So but at some point, right, so it won't just be touching this hemisphere all the way until here. Actually, at some point it will just lose contact with the hemisphere. So and we want to find out, okay, at which angle. Okay, so this particle will lose contact with this hemispherical surface. Okay. And when we will lose contact, right? So you could imagine that when it does lose contact, right? So there will be no reaction force acted on the particle by the surface. So that's why, right? So in this problem, basically needs you to find out the reaction force, okay, acted on the particle by the surface. Okay, then work out how it depends on the theta, and so that you can figure out at what value of theta the reaction force will become zero. Okay, so before I write down the equation, so actually we can ask ourselves one question. Is that so I said that I let the particle to slide down from the top, right? So all the way down, right? So why it cannot just touch the surface all the way until it reach here, right? So why it has to leave at some point? Okay, so is there any intuitive answer that we can think of? Right. So you can see the extreme case actually, right? Is that if you just go ahead and consider the particle, right? So just moving and moving until here. So if indeed it can touch the surface all the way until it reach here. So what does that even mean? So this is a hemisphere, right? So and if it's really moving, touching the surface all the way, so that means it's doing a circular motion, right? So that means that basically at this point, right? So it will only have a vertical component of the velocity, right? So if it is really doing a circular motion, right? So, but is it possible, right? So as it moves, right? So it's just moving like this, and of course, it will have two components of the velocity, right? So it will have this component of the velocity and then this component of the velocity. Right? And you think about the force acting on this particle, right? So again, there are actually two forces, right? One, of course, is the mg, and the other is the reaction force that we want to find, right? So, but well, even you don't know the magnitude of the reaction force yet, but you can just from this picture you can see that the reaction force will always have a horizontal component, right? So that means throughout the entire journey, right? So it has to be always experiencing a horizontal force, right? And that means, right? So the horizontal velocity, right? So of this particle can only be getting bigger and bigger, right? So, but if it follow this circle, right? So if it follow it until here, right? So there's no any horizontal component of the velocity, right? So, and that's why that's impossible, right? So the particle obviously is picking up a larger and larger horizontal component of velocity, right? So, but if it has to stay, always stay at the surface, right? So at some point this will be very small and even no horizontal component of the velocity. So that's why that's impossible. Okay, so now let's actually work out the Lagrange equation. Right, so obviously we are going to use r and theta as the generalized coordinate. Right, so first let me set that at this level the gravitational potential energy to be 0, right? So and then at this level, right? So the height of the particle, what is it? It is r cosine theta, right? So I have this height, then of course I can write down the mgh, right? So that is, right? So the mgh, the u potential energy is this mg r cosine theta, right? And then of course the kinetic energy would be, well, in the polar coordinates, right? So then it must be this form, 1/2 m r dot square plus r theta dot all square. So once again, right? So if it is staying on the surface, right? So you know that r is actually a constant, right? So but as I said, right? So here we just pretend that we don't consider the constraint at this point yet, right? So we are going to write out the constraint separately. Okay, so Lagrangian L is this 1/2 m r dot square plus r theta dot square minus mg r cosine theta. Okay, and then the constraint equation, right? So the constraint equation, I'll just write d as a function of r and theta, which is what is the constraint? The constraint is that the particle is always touching the surface, right? So that is R always equals to A. So that is R minus A equals 0. Right. So again, right, so applying the Lagrange equation, right? So with respect to R and theta, right? So this is the two equations that I'm going to write down. Right. Okay. And then of course the next step is just nothing but taking partial derivatives, right? So then I'll just write them out. First one is this. Okay. The partial G partial R is just 1. Right. So and then the second one, I have this M square theta double dot plus this one. And the right hand side will be 0 because partial G partial theta is 0. And now we'll put in, so at the end, right? So you know that what do we want to find? So at the beginning, I said that I want to find this reaction force, right? So and this N is exactly this one. Okay, I want to find lambda. Okay, the Lagrange multiplier. So now on the side, let me also write down what the constraint equation tells us. Right, so from this one, I'll have R dot equals 0. Right, so R double dot also equals 0. So then let me call this equation 1, this one to be equation 2. And then by equation 2, and putting in this R double dot and R dot to be 0, what you will be able to get is that, right? So this one is 0. So then you'll be able to get that theta double dot equals G divided by A sine theta. Right? Because, right, so R equals A. Okay. So I want to find this lambda, right? So at the end, right? So first of all, I can also just cross out this term. And that's why I need to find this mg cosine theta minus mr theta dot square. Right. So that is, I want to find theta as a function of time. So from here, I want to see if I can do that. So it turns out that it would be difficult to directly find out theta as a function of time. Okay, but we can actually find out the relation between this theta dot square and this cosine theta. So from here, okay, so the left hand side is this theta double dot, right? And this is actually d theta dot dt. And the trick here is that I'm going to use a chain rule. Okay, so to write this d theta dot dt as d theta dt d theta dot d theta. And remember this d theta dt is actually theta dot. Okay. And this whole thing, right? So this whole thing is still equals to theta double dot. This is exactly the same thing. Okay, so and this will be equals to G divided by A sine theta. Okay. So now just look at this one, and well, you can see that you have theta dot and theta, and you can do separation of variable. Okay, so that is you're going to just keep all the terms of theta dot on the right hand side, and then all the terms for theta on the right hand side. Okay. And then you integrate them. Okay. So then on the left hand side, what you get is theta dot square divided by 2. And then on the right hand side, you have this one plus some arbitrary constant. But this arbitrary constant can be found, right? Because when theta is 0, so when it's at the top, right? So there's no velocity. So that's the condition that I gave you, right? So then theta dot is also 0. So using this initial condition, right? So you will be able to find that this C is actually E divided by 8. So this equation over here, okay, if you actually look at the problem again, you actually may see that you can use another way to find out this relation. Okay, that is something you are familiar with already. Conservation of energy. Okay. So if you consider the total energy here, and then the total energy here. So and then you equate the equation, you will also be able to find this relation here. Okay, but now this is good, right? So because although we did not really find out theta as a function of time, right? So but I find out a relation between theta dot square and this theta. And now I'm going to substitute this equation back to equation 1 over here. Okay, so that then the left hand side of this equation 1 will just depend on cosine theta. Okay. So I don't have space over there, but let me just continue here. So lambda would be equals to, right? So mg cosine theta minus ma theta dot square. This is by equation 1. And this theta dot square in terms of cosine theta, then you find that the whole thing is mg 3 cosine theta minus 2. Okay. So from here, what you can see is that this will be the greatest when cosine theta is the greatest. Right? So that is when theta is 0. Okay. So when theta is 0, so that is when it is on top of this hemisphere, and at that time nothing is moving. So first of all, so if you don't look at this equation, right? So initially, right? So you can tell me what is the reaction force, right? So the reaction force at that moment is exactly mg, right? So exactly cancel the gravitational force acting on this particle, right? Then indeed, right? So you can go back to this equation here, right? So if you substitute theta to be 0, so then this 3 cosine theta is just 3, right? So then you have this mg times 3 minus 2. That would be exactly mg, right? So then that is very, right? So that indicate that, right? So this result is very reasonable. Okay. So, and as this lies down, right? So then theta is getting bigger and bigger. Then this whole term, right? So this 3 cosine theta minus 2 is getting smaller and smaller, right? So, and at some point, actually, this 3 cosine theta would be smaller than this 2, right? And that would be when the normal reaction force switch direction. So what it really means is that it goes, right? So maybe it's when it's here, right? So the normal reaction has to be going to the other direction. So what it really means is that if you are not able to provide that, the particle will lose contact with the surface. Right. So then we are, as I said, we are interested in at which angle, right? So the particle starts to lose contact, right? So that's why, right? So I am interested in the situation when lambda equals 0. Right. So, and that would tell you that theta is at the arc cosine of 2 divided by 3. Right. So at this angle, it will lose contact. Okay. Last example for this part of the chapter. Okay, so we'll finish this and then take a break, and then we'll start the part 3 of the chapter. Okay. So this one is a bit special because I'm not just talking about a particle, right? So this is actually a rotation problem. Okay, a disk or a cylinder rolling down an inclined plane. Okay, so what it really means is that the center of mass, right, of the entire disk, of course, is having this linear velocity, right? So, but at the same time, right, so the disk is spinning or rotating about its own center of mass. Right. So I believe that you have learned how to write out the kinetic energy, okay, for such an object, okay, which is rotating, right? So well, this is not just rotating, but this is also having a linear velocity, right? So and I believe that you have learned that for this kind of motion, right? So the total kinetic energy can be written as a sum of 2 parts, right? The translation part and the rotation part, right? The translation is the movement of the center of mass of this system, this disk, and then the second one is the rotation, okay, about its own center of mass. Okay. And therefore, I have this 1/2 m y dot square, and then the other is this 1/2 I. Again, I assume that you have learned that is the moment of inertia of this disk. Okay. So that's why this is what I'm having over here. Okay, so next, right? So is the gravitational potential energy, right? So of course, this time well, although this is not just a point mass, but you understand that all you need to do is to find out really is the height of the center of mass of this disk. Okay. So I want this height. Okay. So here I should have set that, but let's say the total length. Okay, so the total length of this inclined plane is L. Okay. So then this part over here is L minus Y. Okay. And therefore, this vertical height here is L minus Y sine alpha. Okay. And therefore, right, so the potential energy is mg times this. Okay. So this is the Lagrangian I write down. So then what is the constraint in this problem? Okay, first of all, right, so I assume that the whole thing is always touching the surface. Okay, but not only that. Okay, so I'm considering a motion that's so-called rolling without slipping. Okay, so I believe that you might have heard of this term before, but let me just briefly explain it one more time. Right, so it's essentially what happened when we have the cycloid. Right, so do you remember when I talk about the cycloid, how do we make a cycloid? Right, so is that if let me draw again, just for simplicity, I'm just drawing a horizontal floor. Right, so I have this disk or wheel. Okay, rotating. Okay. So initially, so they should be touching. Okay, so but for clarity, I just make a little gap here. Okay. So let's say this. So what is the radius of this thing? Okay, so capital R. Okay. So and this is the contact point with the ground, right? So this is the contact point with the ground. Okay. So rolling without slipping means that there is always no sliding. Okay. So what does it mean by sliding? Sliding means that if I have this entire disk, okay, so to be after some time to be over here, right? So but then this point that I labeled is still over here, then that's sliding, right? So that is that this point, and it's always sliding, having the relative motion, okay, with this floor here. But this is the extreme case, right? So you could imagine that what happened is that this entire disk is just translating, but there's no any rotation at all, right? So then that would be what happened over here, right? So, but if it is not just translating, but at the same time also rotating about its own center of mass, right? So then this reference point that I labeled, okay, will be somewhere maybe over here. Okay. So, and let me draw this vertical reference line. So, and I'm going to call this theta. Okay. So initially, right, so the theta is 0. So over here, this is theta. So if I want to have the so-called rolling without sliding, okay, so what I need is that the distance that it traveled, the whole thing traveled, which is this one. This distance, okay, marked by this green, which I call y, has to be having the same length as this part this circular arc. Okay. And the length of this circular arc is, of course, R times theta. If I have the so-called rolling without slipping, okay, so this is not a good picture, obviously. Then what I need is that this length of the green has to be equal to this length of this purple. So this y equals R theta. That's what I mean by rolling without slipping. So, and therefore, okay, if that happens, right, so this would be my constraint equation. Okay, y minus R theta to be 0. Okay. So then again, right, so here I have in the Lagrangian, I have two generalized coordinates, y and theta. Right, so that's why I have these two Lagrange equation over here. And then again, just taking derivatives, right? So I have these two equations. And then now I also consider the constraint equation. Okay, so then this is what I have. Okay. And the same procedure, right? So I have, I'm just going to substitute what we got from the constraint equation back to the two Lagrange equation of motion. And then I'm able to find out lambda and also as well as the y double dot and the theta double dot. So, and the generalized force, okay, so if I just go back to calculate these two terms, okay, so, and then what I have is these two results over here. Okay. So, the first one, right, so is a partial derivative with respect to some linear distance. So this is actually still means the force, okay. But the second one is the partial derivative with respect to some angular coordinate, okay. And then the second generalized force actually does not have the unit of force, but have the unit of torque. Okay. So what are the physical meanings? Okay. So the first one, okay, so would be the friction acted on the disk by the plane. Okay, so that is this friction here. Okay. This is given by this. Okay. And what about this? Okay, so this one is actually well, we're closely related to the friction, but it's actually the torque due to the friction. Okay, so basically it's F times R. Okay, so you can see that all I have is just an additional factor of R here. Okay. So then you can see that, okay, so this one of these does not have the unit of force, okay, as unit of torque. Okay. And also one remark to make here, although it's not I think you have noticed this before when you learn about this problem, is that in this case, okay, so the friction is not a dissipative force. Okay, what does it mean? So if you go back to what you learned in the Newtonian mechanics, is that this force, okay, does not do work done. Okay, so and it is all because of the fact that this is a rolling without slipping problem. Okay, so if you have a case where you just have the translation but without the rotation, then that frictional force will result in work done. Okay, so now let's take a break. Okay, so we'll come back at 12:30. Okay, so and then we will start the part 3, which is also the last part of this chapter. Okay. Okay, so here comes to the part 3 of this chapter 2. Okay, so it is about conservation laws. Okay, conservation laws, I believe this is not something that actually new to you, right? So conservation laws, so namely, conservation of linear momentum, conservation of angular momentum, and conservation of energies. Okay, so these are the 3 laws that we'll be focusing on. But these laws are something that you have learned. Okay, so and you might even have learned, right? So how to kind of derive conservation of linear momentum and conservation of angular momentum from Newton's law, right? So this part, right? So basically, we are trying to obtain, okay, so the same conservation laws, right? So from another perspective, right? So of course it will be in the framework of this Lagrangian formulation. Okay, so but in particular, right? So we are going to see how this conservation laws comes from. Okay, so the so-called the symmetries of your system. Okay. So well, before I talk about how these tools are related to each other, okay, so let's again do a quick review. So first is about the linear momentum. Okay, so what you have learned before, right? So you have learned that, right? So this is just the Newton's second law, right? So just starting from the simplest case where I just have one particle, but it could be under some external force, right? So by Newton's second law, dp dt equals F, right? P is the momentum of the particle, F is the net force acted on the particle. Okay. So when I say that the linear momentum of a particle is conserved, right? So what I really means is that the linear momentums of this particle, okay, so does not change with time. Okay, right. So whenever I say that a physical quantity is conserved, right? So I mean that, right? So the system itself can be evolving over time, but then that quantity is not changing with time, right? So that is the conserved quantity. Right? So that is, right? So mathematically, if I say that the linear momentum is conserved, right? So then that means I'm saying that this dp dt is 0, right? So and from this Newton's second law, right? So it's very obvious that you need to have this force to be 0, right? So if you want the dp dt to be 0, and that's just what you have learned, right? So multiple times, right? So but if you don't have apply any force on this particle, then the acceleration of this particle does not the particle does not accelerate. So then the momentum of this particle is a constant. Okay. So and just one small reminder again, right? So remember that well, momentum and also force are vectors quantity, right? So when we talk about conservation of momentums, okay, so we also need to consider the x direction, y direction, the z direction individually, right? So for example, if I have applied a force, right? So this is a non-zero force, but then if the x component of this force is 0, right? So but then the x component of the momentum okay, so this is I mean to say dp dt, right? So the dp, then the x component of the momentum is conserved, right? So and but of course, if the other components of the force is non-zero, then the other components of this momentum is not conserved. Need to consider 3 components separately. Okay. So these examples that you have seen multiple times, right? So in these three cases, right? So do we have conservation of momentum, right? So the first one, of course, we do, right? So this is just a free particle, so that means there's no any force acting on it, right? So the all components of this linear momentum of the particle are conserved, right? So, and in this case, if I have this particle in constant gravity, right, this mg, so this time the z component of the momentum is not conserved, right, but still, right, so the x and y component of the momentum are conserved. And what about this one? Right, so this one, again, I have this mg, but not just that, but I also have tension, right? So therefore, of course, first of all, the z component of the momentum is not conserved, but also, right? So if it is swinging like along this y z plane, right? So the y component of the momentum is also not conserved, right? So because of this tension has this y component. Okay, so practically, so conservation of momentum is not too useful, right? So when we talk about solving mechanical problems for one particle, right? So I believe that even when you first encounter the concept of conservation of linear momentum, right? So you know that the usefulness, right? So of using this conservation law, okay, would be seen only when you consider at least two particles. Right? So again, a quick review here. Right, so here I have a system with these two particles. Okay, so again, I allow there may be external force. So that is to say, perhaps this particle is experiencing an external force, which, so this is particle 1, this is particle 2, which I call this external force for particle 1 to be F1e. And then perhaps the other particle, I have another external force for it, which I call this F2e. Okay. But one more thing is that I allow there are internal forces. Okay, so that is, I allow there exists interactions between the two particles. Okay, so it could be gravitational attraction, it could be electrostatic attraction or repulsion, things like that. Right. So then let's say, right, so the two particles, okay, so they are both let's say positively charged particles, right? So that's why they have this action and reaction forces which they repel each other. Okay, so this one I just call F12, and this one I call this F21. Okay, so then these are all the forces that I have, right, for this system. And now if I apply the Newton's second law, right, so for these two particles individually, right, so then this dp1 dt, which is the rate of change of the linear momentum for this particle 1, will be equal to F1, which is the net force acting on particle 1, right, which is a sum of these two forces. And similarly, right, same law apply to the other particles over here. And one thing I've already told you already, I've said already, is that the these two forces, right? So we'll cancel out each other. Okay, so if I sum all the forces in the system, right, because they form action and reaction. Okay. Okay, so now let's say I want to find out the linear momentum of the entire system. That is, I don't care so much about the momentum of the individual particles, but I want to know the sum of momentums of the two particles. So then what I do is that I'm going to just sum these two equations, right? So, and then on the left-hand side, right? So, and after summing, I'll just call this d capital P dt, right? Which is just these two added together. And then on the right-hand side, I have this F1 plus F2, right? So, but F1 plus F2 actually have 4 terms over here. But because of this action and reaction, right? So we know that these 2 terms are cancelled. Then now on the right-hand side, I have this capital F, but this capital F is just a sum of the external forces only, right? So, but not the internal forces. So now, right? So from this equation here, we see that if the net force of acting on the entire system is 0, right? So then the linear momentum of the system, capital P, is conserved. Okay. So, and again, of course, when we talk about conservation of linear momentum, we need to consider the XYZ component individually, right? So then these 3 examples. So what do we have, right? So this 2 particle collision problem, right? I believe maybe the first type of problems that you learn when you learn about the conservation of linear momentum, right? So in this case, we don't have any external forces, right? So that's why in this case, of course, the conservation of momentum holds, and the internal force, right, only appears when these 2 particles they hit each other, right? So, and the second one, right? So this one is the example that we did right before the holiday, right? So this particle sliding down, and then this wedge is free to slide on the table, right? So in this case, clearly, so we have we don't have conservation of momentum in the z direction. Okay, so but in the horizontal direction, okay, we do have conservation of momentum, right? So we still remember that when the particles slide down, it has this momentum to the left, and then on the other hand, this wedge will move to the right, so it has momentum to the right, right? So you can go back to that problem and verify by yourself that this momentum plus this momentum is indeed 0. Okay. So, and this one, right? So it's also an example that we have talked about, right? So it's very similar to this one is that we don't have conservation of momentum along the direction of the gravitational force, but we do have conservation of momentum along the horizontal direction. So these are just small examples, right? So if you have 2 masses, right? So attach it to the 2 ends of a spring, right? So and if there's any external force, then again you have conservation of momentum for the entire system, right? So you could imagine that if you compress the system, then what they do is that they will oscillate out of phase, right? So that is when this particle moves to the left, the other particle move to the right, right? And then after some time, the particle on the left will move to the right, and then the particle on the right move to the left, right? So and then if I consider this so-called a binary star system, right? So just imagine there's two stars orbiting around this common center. Okay, so then again, what I have is that just the internal forces, the attraction between the two stars. I just ignore all the other forces, right? So in this case, I also have conservation of linear momentum. So then here, right? So just a straightforward generalization, right? So if I have an n particle system, right? So again, all I need to consider is the net force, right? So acting on the entire system, right? So consider the net force acting on all the n particles, right? So if this is 0, then the total momentum, which is the sum of the n momentum vector, okay, so will be conserved. So now I want to go back to the Lagrangian formulation here, right? Is that if I go back to the one particle system, if I consider this particle in a potential, right? So then the Lagrangian in the generic form looks like this, and the three Lagrange equations given over here, and last time, right? So last time I told you that this px, py, pz, right, so are given by these three partial derivatives here. So now I want to consider, right? So whether the momentums are conserved or not, right? So if I just take one of the equations out, right? So if I want to ask whether the z component of the momentum is conserved or not, so that means I'm asking whether this time derivative, right, is 0 or not, right? So it really depends on this term, right? So if this partial L partial z is 0, then you can say that, yeah, this momentum along the z direction is conserved. Right? So that is, right? So in other words, right? So if in this expression of the potential, right? So if it actually does not depend on one of the coordinates, right? If it does not depend on z, then actually the momentum along that direction will be a conserved quantity. Okay. So and in fact, okay, so the coordinate that does not appear in this term, okay, is called the cyclic coordinate, or known as the ignorable coordinate. Okay. Right. So okay, so one simple example over here is that well, this again, this particle in constant gravity in the z direction, right? So and here, so you can see that the potential term, right, so does not depend on x and y. So and because of that, right, so we can say that this px and py are conserved, or we say that this x and y are the two cyclic coordinates. Okay. So and in a more general sense, okay, so suppose my Lagrangian is expressed in terms of a set of generalized coordinate qi. Okay. Then if the generalized momentum, okay, this partial L partial qk dot is conserved. So then that would happen when this one of the coordinates is a cyclic coordinate. Okay. So then you could imagine that this because of this generalized coordinates, right? So it does not always have to be corresponding to linear momentum. Okay, but here, okay, in this lesson we will still be focusing on linear momentum, but the next time, we'll also talk about the conservation of angular momentum. Okay, so now well, in the beginning of the chapter, you see the words symmetry. Okay, so now we want to talk about how it is related to the conservation of momentum. Okay. So, and in fact, so in particular, okay, for linear momentum, okay, we say that linear momentum is a consequence of the so-called translational symmetry. So, but what does it mean by translational symmetry? Actually, quite very easy to understand. Is that if you look at the system, okay, and if it actually does not depend on one of the coordinates, so then what it means is that if you change the value of that position, x position by some amount, right? So then that system will not be changed. Okay, so that is the Lagrangian is the same after you change the value of that coordinate. So that is essentially is the definition of translational symmetry. Okay. So if I just go back to this example, right? So here, well, so I have this particle falling down, right? So just to make it realistic, let me draw a floor here. Okay, so a translational symmetry, right? So is that if I am going to translate the system, right? So along one direction, let's say if I translate the system, so that is the system here only has one particle, right? So that means that if I translate this whole thing over here, so because in this case the gravitational force is just always pointing to the z direction, or in other words, right? So the gravitational potential only depends on this z position, but it does not depend on this position, right? So that means that if I am going to translate this system, right, so left or right by some amount, I would say that the system is still the same, because the Lagrangian that you can write down is still exactly the same. Okay, so that's the essentially that's the very simple example to illustrate what do we mean by translational symmetry. So, but that's a very intuitive. But let's do something that is mathematically more formal. Okay, so that's what I'm going to introduce next is a concept known as the virtual displacement. Okay, so I give you this system. Okay, I give you this system, and then I will do an operation which is known as the virtual displacement. Okay, so and then after I do that, okay, so we look at the Lagrangian again to see whether it has changed. Okay, so that's the goal. Okay, so if it does not, then that means the system has translational symmetry. Okay. So here, okay, so this slide is a bit wordy, but just let me just lay out the definition first, and then I will explain it. Okay. So so what is a virtual displacement? Okay, so we are just going to give a very just the basic definition, but we are not going to apply it to a very complicated problem. Okay, so if you have read some advanced level mechanics books, okay, maybe you'll see an entire chapter about this virtual displacement and virtual work done and so on, but we are not going to be that going to that deep. Okay, so but let me just finish the definition. Okay, so and then I'll try to illustrate with some pictures. Okay, so definition. Okay, so a virtual displacement. Okay, a virtual displacement can be in any direction that you pick. Okay, so let's say along x direction. Okay, is an infinitesimal instantaneous displacement. Okay, and such displacement must be consistent with any constraint acting on the system. Okay. So so first of all, I want you to just kind of forget about the second sentence here, because the topic that we are going to talk about won't be including any constraint anyway. So we'll just consider particles, okay, under some in some potentials and with some internal interaction, okay, but forget about constraint. So then just focus on this first sentence. So it's an infinitesimal instantaneous displacement. Okay, so what it really means, okay, again, let me try to again use the most simple example to explain this. Right, so just a particle falling down. Okay, so again, I have this uniform gravitational force mg. So first of all, what is an actual displacement? An actual displacement is something that it actually do over time, right? So at some time t is over here, right? So after some small amount of time dt, okay, you know that it will be over here. Okay, so and let me call this displacement, which is really happening, right? So to be dr, okay, and this dr happens within an infinitesimal amount of time dt. Okay, so that is something actually happening, and so the actual displacement will happen because of the fact that this particle is following the dynamics of the system, right? So it's under this force, that's why it has such a displacement. Okay, so if it keep falling it down, so what it won't do is that it won't go like this, right? It won't do this, right? So unless you have some initial velocity in the horizontal direction already, but if it's just falling down all the way, so then it won't suddenly just shift to the left or to the right. Okay. So but now let's talk about the so-called virtual displacement. Okay, the virtual displacement really means something that is arbitrary, and we imagine that it happens. Okay, but that displacement does not really follow the dynamics of the system. Okay, so that is one picture to think about is just imagine. Okay, just imagine that we kind of have some kind of superpower to actually freeze the system in time. Okay, we freeze the system in time at a particular moment, and then we are able to just displace this falling particle to another position over here. Okay, so I call this delta R. Okay, and then after that, we unfreeze the system, okay, and then allow the particle to keep going, okay, according to the dynamics of the system. So this delta R, okay, happens at no time, right? So as I said, right, so you imagine that you are able to freeze time, and then you do this, and then you unfreeze it, and then you allow it to evolve again, right? So, and this delta R, right, is something that you can pick arbitrarily. Okay, it does not have to be go like this. It can be goes like this, or you can also make it go down. Okay, and this so-called virtual displacement, okay, does not change the velocity of that particle at that moment. Okay, all you do is that you just move it to somewhere else. Okay, and then you unfreeze it. So at that moment, V is not changing. Okay, But after you let the system evolve again, we can change according its own way. Okay, but that's something happens later. Okay. So then this, when we talk about this virtual displacement, okay, so I will use this notation delta R. Okay, so to distinguish it from the displacement dr. Okay. So, and this dr, right? So as I said, right, dr really means the displacement happens, right? So within an infinitesimal amount of time dt, right? So this dr dt has real physical meaning. So, but as I said, this delta r happens at no time. There's no dt or no delta t correspond to this delta r. Okay, so then these paragraphs, okay, just basically repeat what I just said. Okay, so but one more thing, and again I also talked about already, is that the virtual displacement can be in any direction we want. Right, it does not have to be dx, does not have to be just, it does not have to be just in x or just in y, right? So it can be in any arbitrary direction. Okay, so then in general, I'll just call this virtual displacement to be this delta r vector. Okay, written like this. And these three components, okay, so are independent. Okay. So now let's see how the Lagrangian would change. Okay, after we applied such a virtual displacement. Okay. So by definition, okay, so remember this Lagrangian is a function of x, y, z and then x dot, y dot, z dot. So after we apply the virtual displacement delta r, right? So the Lagrangian becomes this. Okay, the first term here. So I want to find whether the Lagrangian has changed. Then what I do is that I take this term, okay, so and then minus the original Lagrangian. So that's I call delta L. Okay, the variation or the change of the Lagrangian due to the virtual displacement. So here you can see that this L, right? So I have this x become x delta x, y becomes y plus delta y, and so forth. But you can see that this x dot, y dot, z dot are still then, okay, unchanged, because I told you already, by definition, virtual displacement does not change these quantities at that moment. Okay. So then here, what I do, okay, so is that you just recall the concept of total differential. Okay, recall the concept of total differential, then I'll be able to write down this delta L to be a sum of these three terms. Okay. And then one more manipulation is that I'm going to write it in this form of a product or dot product between two vectors. Okay, so this is a better writing here, because now I can really see the term of this virtual displacement by itself. Okay, over here. Okay, so now this is what we'll be using. This formula is what we'll be using. Okay, so if I have given you a Lagrangian, okay, L over here. Okay, so I want to find out this delta L. So first, let me write down this partial L, partial x, partial L, partial y, and partial L, partial z. Partial L, partial x, of course, is just 0. Partial L, partial y is also 0. And then partial L, partial z is minus mg. Okay. And therefore, right, so this whole thing is just minus mg z hat. Right. So now I want to find delta L, right? for these two cases. Right, so the first one is that delta R is given by delta x hat, and the second case is this delta R equals this delta z hat. So these are arbitrary, right? So I want to pick this, so that's why they can be anything that you want to pick, right? So it can also be delta x hat plus delta y hat. Okay, but then for part A, right? So these are very easy to do. The delta L would be, right? So it would be minus mgz dot delta R, which is delta x hat. And this z hat dot x hat is 0, right? So then this delta L is 0. And for part B, right? So this delta L again is this minus mg z hat dot, but this time is delta z hat. And this is non-zero, it's minus mg delta z. Okay. So then these two exercise, right? So tells you that, right? So for this system, right? So it has translational symmetry along the x direction, right? So but not along the z direction. Okay, so it seems that we have kind of a more just a fancy way to express or to so-called test the symmetry of the system, but it doesn't seem to be so much useful practically, because right, so if I just look at this by itself, I know that it contains z but not x and y, then I can immediately say that it has translational symmetry in the xy direction but not z. Okay, why do we bother to introduce this virtual displacement? Okay. So if I go to again more complicated case, okay, again we may appreciate how it is useful. Okay, again two particles. Okay, so if I have two particles, then I have these two terms for this kinetic energy, and then minus this potential term. Okay, so this potential I just write as one term, but it can contain multiple terms, right? So first of all is the potential energy of this particle, right? So due to the external force, and then the potential energy of this particle also due to the external force, but also the potential energy due to the interaction between the two particles. Okay, so then that actually can be like maybe three terms. So here, okay, so again, I want to test whether this particles, these systems has translational symmetry. Okay. So now this time, if I want to make the virtual displacement, okay, for this system, I have to do the virtual displacement in the same way for both particles in the system, right? So that's the meaning of translating the system, right? So if you want to move one, then you have to move the other also exactly the same way, right? So that is, if I apply this delta R for this particle one, then I have to apply the exact same delta R for the other particle. So that is for the whole system. So now I'm going to take the Lagrangian, right? So apply this x1 becomes x1 plus delta x. This y1 becomes y1 plus delta y, and so on. Okay. Okay, so here I'm just being lazy. I should be really writing x1, y1, z1 x2, y2, z2. Okay, but you understand then what I mean over here. Okay. So, but with that, if you are going to again use the total differential, okay, so you'll be able to see that this time there are 6 terms coming out. Okay, the 3 terms for the 3 coordinate of the first particles, and then the other 3 terms for the 3 coordinates of the particle 2. Okay, so now I'm going to rearrange the terms. Okay, so again, write this as group the first 3 terms together to write it as a dot product between 2 vectors, and then the last 3 terms together, okay, as a dot product between 2 vectors. Okay. And but then the nice thing is that this I also have further can be group them together, right? Because I have this delta R here, also the delta R over here. Then I can really group what I have from the previous slides into just a big dot product. Okay, so is this big terms, okay, a big expression here dot this delta R. Okay. So now, right, so if I have a translational symmetry of this 2 particle system, right, so what it really means is that delta L equals 0 for any delta R. Right, so that is no matter what direction of delta R I pick, I require this delta L to be 0. So that means this whole thing has to be 0. And that also means that this component is 0, this component is 0, and this component is 0. Right, so then that's what I have over here. Okay. And from the Lagrange equation, okay, again, remember this partial L partial x1 is my dp x1 dt. Okay, this partial L partial x2 is my dp x2 dt. Right, same thing for the other 2 components. Right, so from here, right, so you can see that you can see that what we have are the conservation of momentums for the total system, conservation of the total linear momentum for the system. Right, so in the you can see that well in the 2 particle system, right, so you can it's most of the time is really more difficult to say that okay, it does not depends on 1 or 2 of the coordinates, right? So instead, right, so we need to really look at these terms together, right? So let me go back to this 2 examples that you have seen. Okay, so this, right, so these 2 masses with a spring, right, so from our intuition we already know that the total momentum of this system is conserved, right? So but of course if I write down the Lagrangian, okay, if I write down the Lagrangian, okay, so it really depends. There's no ignorable coordinate, right? So because, right, just to make it simple, if I just consider this one as a 1-dimension problem, let's say I just 1-dimension problem, so that means that the system just move on a line, right? So that is let me say that this is x1 and this is x2, okay, and then the Lagrangian would be, right, so it would be 1/2 m x1 dot square plus 1/2 m x2 dot square minus this u term, right? So in this case, right, as I said, there are no ignorable coordinates, right? So it really depends on both x1 and x2. Yet, you know that this entire system, right? So the total momentum is conserved. Okay. And you can, of course, again do the exercise, right? So just to take this Lagrangian and then try to do all these three partial derivatives, well, not all three, but just the first one, you can really verify that this is zero, right? And this one might be more complicated, but this R1 minus R2, right? That is the relative distance between the two stars, right? So actually, it can be written as this. Right. Again, you may try to take this Lagrangian and then take these partial derivatives to verify that they are all zero. But of course, right, so in this special case, we really don't need to do that to know that there's a translational symmetry, right? So because if I have a potential that can be written as a function of the relative distance between the two particles, right? So if I can write down a potential that in this form, right? So then you know that it always has translational symmetry. Why? Because if I go to consider this R1 plus delta R, right? If I translate the system, right, give the virtual displacement, then you can immediately see that this delta R1, of course, will cancel with this delta. This delta R, of course, will cancel with this delta R. Right. So after the virtual displacement, you will still get the same potential. And that's why the Lagrangian is does not change. Right. Okay, so one last slide over here. Right. Just again, well, I'll just say this is again a straightforward generalization of for n particle systems. Okay. So if you just apply again a virtual displacement delta R, right, to this n particle system, again, remind you again, that means that you apply this delta R for all the n particles in the same way. Okay. Then you can show that this delta L, okay, so it's given by this whole vector dot this delta R. Well, again, if this system indeed has translational symmetry in all directions, then delta L has to be equal to 0 for any delta R. Okay. So that is, right, so this whole thing is 0, this whole thing is 0, and this whole thing is 0. And that would, again, give you, right, so the total x component of the momentum is conserved, total the y component of the total momentum is conserved, and the z component is conserved. Okay, so then that's all about. So I think in this chapter the things may be a bit abstract, okay, and it doesn't really gives us the new physical laws, right? So conservation of momentum, we still just use conservation of momentum, okay. But here it really just to show you how we see the conservation laws, okay, from the perspective of the which is the so-called the symmetry of the system. Okay. So next time we'll continue on talking about how conservation of angular momentum, okay, related to the rotational symmetry of the system. Okay. And also we'll talk about the conservation of energy. So, and I have to add that the concept of virtual displacement, okay, won't be in the homework or exam anyway.